Hi everyone, today we're going to talk about transformers. I'm going to give you some tips and tricks on how to discern between, say, filament transformers, power transformers, audio transformers, chokes, interstage transformers, and all that kind of stuff. We're going to also talk about the wire color coding on transformers, and that really is the key in finding out what a transformer does. A lot of the times, the colors of the wires give things away. I'll talk about the common colors and how they've kind of changed things over times and things like that. And then what I'm going to do is I'm going to show you how to calculate impedance on an audio transformer. We'll talk about the differences between impedance and resistance. A lot of people seem to get that confused, and you'll see that there is really quite a difference. Now, there are a lot of people that try to show how to calculate the impedance of an audio transformer, and they really make it look like a difficult procedure. Why? I have no idea. It is incredibly simple to figure out what should be on this side of the transformer and what should be on this side of the transformer. We'll talk about that as well. So that'll be very, very beneficial if you're an audio amplifier builder or if you're just, dealing with transformers in general. So we got lots of transformers to take a look at. This is only some of them. I have some off to the side here as well. So we'll take a look at all these different types of transformers. We'll talk about their leads and just discuss the transformers in general. So let's get going. This is the first transformer that we're going to take a look at today. Now, the first thing I can tell you about this transformer is I already know what it does just by its size and the lead coloring. You're probably saying, oh, how can you tell all of that just from something so simple? Well, there are a lot of similarities in these transformers, and throughout time, I'm going to pass this ability on to you. We'll take a look at audio power amplifiers, power supplies, receivers, transmitters, all sorts of things, and you're going to start to notice where the transformers are situated on the chassis and what the lead coloring is of those transformers, and you're going to start to see the similarities in the actual transformers themselves and the lead coloring. Here's the thing. Nowadays, with a lot of the modern power transformers that are offshore, they don't seem to be really caring about the lead coloring at all. It seems to be whatever spool of wire they have on the bench at the time they're winding the transformer. But a well-known transformer manufacturer like Hammond will have a color coding for their transformers, and it makes this really simple. A lot of the audio power amplifiers and a lot of transmitters, receivers, and things like that have these types of transformers in them, the color coding is pretty standard, and you'll be able to recognize this at a glance. For those of you that want to guess what the leads do, where they go, and what the transformer is, pause the video now and take your guess. And for those of you that want to know right away, here is the answer. So by looking at the lead coloring, black is very commonly running off to the AC line. I'll talk a little bit more about the commonly here in just a little bit. These commonly run off to the AC line. And whenever you see green leads, they're usually filament leads. So whenever you see two solid colored leads like this, and one of the same kind of colored lead with a stripe on it, the solid colored leads are the ends of the winding. And whenever you see a stripe, that's usually the center tap for the winding. So this would be for, say, a balanced filament system. This would run off to, say, the chassis. So you wouldn't have a hum balance pot in, say, if you're using this as a filament supply in an audio amp or something. You would not have a hum balance pot because this is kind of, I guess you could say, automatically doing that. So what you do is you tie this to the chassis, and then these would run off to the filaments of all of the vacuum tubes. Now, whenever you're testing a transformer like this, you can very easily do this with a Variac and isolation transformer and a dim bulb tester. So what you would do is you'd have your dim bulbs in line, and you feed the AC to this side, and you slowly turn the Variac up, and you watch the bulbs. If the bulbs don't light very bright, you're on the right track. If you turn the Variac up just a little bit and the bulbs get really bright, that they've wired the transformer in an odd way. And I'm going to talk more about that in the future. We're going to actually go about dim bulb testing all sorts of transformers, and I'll show you the procedure for that. Now, that is a risky procedure, and if you're going to ever be using a Variac, an isolation transformer, and a dim bulb tester to verify or to test any type of transformer, you're doing so at your own risk. There is, high voltages and currents involved whenever you're doing this, and if you don't know what a transformer is doing, it can be very, very dangerous. So say these leads on this side were red, and then say red with a yellow stripe, that could mean that this is an extremely high voltage transformer. So you might put, say, 120 in on this side and get 750 out on this side. So you really have to know what you're doing. Some of the the more modern transformer manufacturers, and some of them that are not following the rules, will just put any color in on any side. So you could even have 750, 1000 volts, something like that out on this side. So you need to be very, very careful when you're testing. And of course, if you don't know what you're doing and you feel that you're putting yourself at risk, never ever take the chance. Don't do that. Because as I say, there's a lot of current available at some of these transformers. And I'll talk a little bit more about that here in just a little bit. So this is the thing to remember right now. Okay, so this is a common occurrence amongst transformers. Whenever you see black leads like this, usually AC line. Whenever you see green leads like this, you know that the two solid colors are the ends of the winding, and whenever you see the stripe, it's a center tapped. So green leads are very commonly filament lines whenever you see a transformer like this in a chassis. So this would be a separate filament transformer for something. So say there was a high gain stage or something like that somewhere, and you needed a separate filament transformer that was isolated from the rest to keep hum down, something like that. That's where a transformer like this would most likely come in line, or anywhere you need a separate type of filament transformer. So that's the first transformer. Let's take a look at the next one. Here is item number 2. So what is this? So we see that there's a winding on here, but there is only 2 wires coming out of this winding. So right there, we know that this is a, pause if you want to guess what it is. This is a filter choke. So this is used in the power supply of many, again, audio amplifiers, radios, transmitters, things like that, anywhere where you need a filter choke installed. And I'll talk more about the purpose of filter chokes here in a bit. So there's just one winding. It's very easy to tell. Just 2 black leads. Now, even though this is a filter choke and there is 2 black leads, we know that there isn't a secondary winding on this or anything like that, right? So 2 black leads in this case are not the AC line. By looking at the device, we can clearly see that it is a filter choke. And these things here can make high voltage as well. You can very easily make high voltage from old filter chokes. And in the future, we're going to design some supplies that do that. In fact, I might have some stuff here where I can very quickly show you how this will create high voltage. There's some stuff around here. Okay, so here we go. I got a neon bulb. Right, so neon bulbs will light at about 75, 80 volts, something like that. I'll grab some test leads. Okay, so watch this. So I'll put this on here. I'm just going to put it right across the leads, like so. Okay, oops. Put this right across here, like that. Hopefully I can pinch them both so they're tight. Boy, this is really not cooperating today, is it? There. Well, we'll just leave it like that then. And another one here. Okay, so that's across the leads. Let me bend this so you can see it. And then in the shot there. It really isn't cooperating today. They were supposed to remain tight, but they didn't. Okay. And what I'll do now is this into the shot here. Just get a 9-volt battery. Now, if you do this at your own risk. Right, this is just basically I'm shorting the choke out and then taking the short off. So you can see here. Lighting that neon bulb up. That's creating high voltage. So what's happening is basically I'm charging it, and then when I remove the lead, like so, see, I'll charge it up and remove the lead. You can see what's happening is the field is collapsing here, and it's releasing a charge out of these wires here, creating high voltage. So it's actually lighting this bulb. So if I was to hold these wires while I did that, I would get a mighty bad zap. Again, don't try this if you're not familiar with this. So you can see. So it's lighting that bulb up. So anyways, this is a filter choke, and you can make these into power supplies for, you know, smaller, let's just say you had a battery operated radio or something like that that had tubes in it, or say you needed high voltage supply for Nixies or something like that. Just taking an old choke like this, you can turn this into a high voltage supply very, very easily. And we'll design some of this stuff down the road together. So nice little filter choke right here. So that's what this thing does. Fits in power supplies and acts as part of the filtering in a B+ supply. Here is our next subject. So we want to take a guess. What is this? Well, what this thing is a push-pull audio output transformer. Whenever you see this lead color combination, this is very common for the vacuum tube side right here, what you see right over here. So red goes to the B+, so this goes to the power supply, and whenever you see a blue and a brown lead, these run off to the plates of the audio output stage. So this is a push-pull audio transformer. This is very common color code for a push-pull situation. And these here run off to the speaker or to the load. Now I'm going to talk a little bit more about audio transformers and determining impedance and things like that here shortly. So this is a push-pull one, and let's see, I do, right over here. We take a look at this one right here. We can see it very clearly says 0 and 8, so we know that this is intended to run an 8 ohm speaker. There's only 2 leads on this one, so this is known as a single-ended audio transformer. So this one here would run off to the power supply, just like the red lead, and this runs off to the plate, just like this one would right here. So not a push-pull situation, a push-pull situation right here. That's these two types of transformers. You'll very commonly see these. The lead coloring on the secondary side changes a little bit. Sometimes you'll see a black, a green, an orange, and sometimes a yellow lead, just depending on how many taps there are on the secondary side. And we'll cover more of that in the future. We have those really large Bogen amplifiers that we're going to go through, and we'll tear them down, take the parts and pieces out of them, and do some experimentation and see what the plate-to-plate load is and everything like that on the vacuum tube side here in the future. So there's a lot of really neat stuff coming. We'll measure the power transformer as well, see how many volts the thing actually makes. I think in the Bogens they may use a doubler. So we'll take a look at that in the future. At any rate, there are 2 audio transformers, really quite common in the older stereo and monaural type audio equipment. Here is our next subject. So what is this? So we have green, black, and yellow on one side, and we have red and blue on the other. So if you want to take a guess at what this is, pause the video now. So from looking at the previous audio transformer, we had red and blue. So we would obviously know that that runs off to the vacuum tube side, to the plate side. So this would go to the B+, and this would be to a plate. So what would these 3 leads go to? These are kind of uncommon colors, aren't they? Well, this is very commonly used. This color combination is very commonly used in an interstage transformer situation. So this would be the center tap. This would run off to either a negative bias supply, or this would run just to the chassis, and this runs to the grids of some power tubes. So very commonly used in Class B driving audio situations. So this comes out of a transmitter. This comes out of and actually comes out of an E.F. Johnson transmitter. This is the interstage transformer. So this is a real common color code for interstage transformers. Whenever you see this on one side and this on the other, you know that this is connecting the plate of a driver tube to the grids of the next stage. This would be driving the power tubes that would drive a very large audio transformer. And that's what an interstage transformer looks like. Here we have another type of, if you want to guess, pause this. Here we have another type of interstage transformer. So this one here is not designed for a push-pull situation. This is designed for an audio situation where there's, say, a single-ended. So this will only attach to the grid and to ground or to a negative bias supply. And as you can see, we have a red and a blue lead here again. And because we have red and blue, we know that this obviously goes to the B+ and to the plate. So this is just a single-ended interstage transformer. A lot smaller too as well. That's what that is. This thing is a monster. Weighs quite a bit as well. This is one of those transformers that has seen some weather, it looks like. So, at any rate, what can we tell from this already? Well, we know that this is a multi-tap transformer. That's pretty self-explanatory from what we've already seen. You can see here on the transformer, that we have two very thick green leads. Right there, that tells us two thick green leads are what? The filament leads. These are really large filament leads right here. Now we have a whole bunch of other colored leads. Just from looking at this, we can already tell this is an older transformer, so we have two black leads right here. What does that tell us? This is the AC line. So we know that this is the AC line. We could twist these together, and we would verify this again with a dim bulb tester or something down the road. So you can twist those together so we know what those are. So usually what I do is I'll just twist them together. We have two red leads on this. This is a very big transformer, and these are two red leads, which means that there is some pretty scary voltage, I imagine, lurking in this when this is powered up. So these would be very, very dangerous leads. This is something that if you were to dim bulb test this or just, test this in general, you'd want to be very careful with these leads because the end-to-end voltage can very easily exceed 1,000 volts on a transformer like this. One of these are going to be a center tap. I imagine this one here, because this is the odd color out of the bunch, might be the center tap. And we have two thick leads, which are the same size right here. So these ones here, actually this one here is pretty much the same color as this one here. So we could very easily verify that. And then this would be the odd color out. This is a thinner lead than the rest. This is going to most likely be the center tap for that high voltage supply. And this can be very easily determined with a DMM, a digital multimeter. So you can test between here, and you'll get half the reading that you would get from here to here because this would be a center tap. In fact, what I'm going to go do is grab a DMM right now and we'll just check that. Let's determine whether this is the center tap for these red leads here. So in order to do this, we're just using a regular ohm meter and there's nothing attached to the transformer. So let's read the end-to-end resistance of these red wires. So this will be end-to-end. And it's about 39 ohms. So if we want to measure from this to one of these leads, and this was the center tap, what are we going to get? Well, we should get roughly half of that. It just depends on how they've wound this. If it is the center tap, and there it is, 20 ohms. So we can tell that this is definitely the center tap for these two leads right here. So what I would do is just take these and twist them together so I can remember that for the future, something like that. Like that there. And we can see that over here, we have these two wires, which are roughly the same color and the same size. We can test these here. They're most likely going to be part of the same winding. Yeah, look at that. That's really low. It's going to be a lower voltage winding there. See what these are. This could have multiple filament windings in this. What is this here? Yeah, that's really low as well. Very low. And reading this is, again, just going to look like a dead short, right? Because there's just a bunch of turns in here to create about 6 volts, 6.3 volts. So that's that. So pretty easy to determine the center tap for this over here. Again, just using common sense and looking at the wire colors and coding. So we're just looking for matched pairs, really. So these two are a matched pair right here. These two are the same color, so we know that those are going to be a match. These are going to be a match. We have two black ones here. And then, of course, what are we left with? We're left with 3 wires. Very commonly in a power transformer like this, you have a center tap on the high voltage winding, and that's exactly what this is. You never want to do this type of a test with any type of voltage or current applied to the transformer because that could be a very, very dangerous situation. So you always want to make sure that the transformer is completely disconnected from anything before you test anything the way that I just did. Again, this is just an ohm test. That's all we did. We just did an ohm test here. No voltages or anything, no current is present on this transformer or coming out of this transformer. I had to zoom out for this transformer here a little bit. So, from what we've already looked at, what can we tell from this transformer here? So you might want to take some guesses. If you do, pause the video and I'll explain this now. So we have 2 really large green leads on this side, and we have a green lead with a yellow stripe. So what does that tell us? Well, first of all, we know that these are the secondary side here, and these 2 large green leads are going to be the filament supply for some very large vacuum tube or vacuum tubes. This will be the center tap. It's a really small lead. The reason that the center tap is smaller than these leads here is because there is very little current passed through this. So just say that this was attached to some large RF output tube or something like that. The only current passage that would come through these leads and out this to say the chassis would be the cathode current, which is, most likely going to be under an amp of some sort, and this will very easily carry 1 amp. The bulk of the current that needs to light the filament in the tube is carried by these two very large wires right here. And as you can see, these would pass a lot of filament current. This is a really large transformer. Since this is a larger transformer, we can see on the primary side here that we have lots and lots of wires. And since we have no data sheet on this transformer, how are we going to figure out where all of these wires go? Well, I'm going to show you that right now, and you can use this procedure for other transformers as well if you have these things laying in your junk bin. First of all, we want to use all the clues that we can get from the transformer itself. So if we read the tag here, it says 110 to 240. You can see that on the tag there. Kind of glary. Under the light there, it is 110 to 240. So we know that since this is 110 to 240, there's a really good chance at this point that we have two primary windings. So if we were to run this at 110 or 120, say, we would run the windings in parallel. And if we were going to run this at, say, 240, 230, 220, whatever is available, we're going to run a portion of these windings in series. And again, that would be a portion of the windings in parallel as well if it was, going to be run at 120, right? The leads that aren't used are going to be basically capped off or disconnected at this point. You wouldn't want to tie those leads to anything else. Now, we can see that we have two sets of leads running into the transformer, one running to this side and one running to this side. And, that could be a little bit, confusing. You might think, oh, okay, one winding's here and one winding's here. But if we look at the color coding of the wires, it clearly doesn't jive. We have a red and a black here, but we have a red on this side. We have a yellow and black, and then we have an orange, a brown, and it's kind of all over the place. A solid black wire here. So in order to really know what we're doing, we really need to spend some time with a digital multimeter and try and figure this out. You can see they tightened that down tight, didn't they? The core is bulging here. That is nice and tight. They've pinched this together really good. Yeah, that is definitely tight. So let's figure out what the primary is on this thing and go from there. The first thing that we want to do with this transformer is draw what we already know. So we know that we have a secondary winding and a core. So let's draw that on the piece of paper here. So draw a nice big core here because we don't know how we're going to draw the primary. And I'll give the secondary 3 turns. Let's say 3 turns right there. That should be okay. Make this one the center tap. That worked out. So we know that the solid colors are the ends, green and green. And we know the center tap is green and yellow. So, green and yellow. Pardon my horrible writing. And that's what we know about this transformer so far. We don't know much about the primary other than we have a whole bunch of wires. Are they 2 separate windings? Are they one solid winding with a whole bunch of taps? So how we're going to locate this right now is we're going to see if we can find an open connection between at least 2 of these wires. If there is, then we know we have 2 separate windings, and then we can split the windings up. So let's find out. So I'll attach my lead to brown, and let's say, let's just try this one here. Oh, there's a connection there. So let's go between brown and black. Aha, no connection. So we have 2 separate windings here. Now, if we count the leads, we have 1, 2, 3, 4, 5, 6, 7, 8 leads. So if we have 2 separate windings, we can already draw this. So we'll just go 1, 2, 3, 4, 5, 6, 7, just because. 1, 2, 3, 4, 5, 6, 7, just because. So we have 2 windings, so we already have 4 leads taken up, so we only have another 4 leads really to try and figure out in this. What we want to do first, though, is we want to find all the leads in one winding, and then that'll tell us that all the remaining leads are in the other winding. Pretty simple, right? So let's just pick one wire. So let's pick the brown. This one, just because. So I got brown. So if I touch a striped lead here, I have a resistance reading. So what I want to do now, because this is one winding, is just twist these two together like so. So to organize this, okay? So from brown to orange is no connection. From brown to black with an orange stripe is a connection. So I'm already seeing a pattern here, stripe leads. So these are part of this winding, and we have another striped lead here. I wonder if it's going to be part of this one. So let's go from this one to the brown one, like we had before, and there it is. So there's our pattern. So all of these leads here are one winding. That leaves these leads right here. So now if we look at these leads carefully, we can see that we have red, orange, and yellow stripe. And in this winding here, we have red, orange, and yellow. So you can see this is the common, I guess you could say the similarities between these two windings here. And then we have one out color. And then the one out color on this side is going to be brown, right? So that's just looking at the similarities. So the striped leads, we have yellow, orange, and red. We have yellow, orange, and red on this side, and then the one out color. So most likely the one out color is going to be the far end of the winding. So let's just make sure that all of these leads have continuity first. So I'll just go from here to here. Yep, continuity, continuity, and then to the yellow one here, continuity. And now if I go to the opposite side, to the other winding, I should have no continuity. And as you see, there is no continuity here whatsoever. So we definitely have two separate windings. So this is one winding here, and this is the other winding here. So now, if we use the resistor color code to also kind of give us a hint, we know that red is number 2, orange is number 3, and yellow is number 4. So we have brown, which would be number 1. So this is the odd color out, because again, we have these 3 common colors and these 3 common colors with the one color out black, which is, in the resistor color code 0, right? So let's use this side here first, because this is the easiest to see these colors. So I'll just get this kind of out of the way. I'll twist these just a little bit tighter, and then I can kind of unravel these ones a little bit here so that we can see what's going on. You can also see that the wires are crossing each other. So we couldn't say that, all the wires run into one side of the winding or one winding and all the others that go onto this side or the other. You can see they're crossing over. You see the striped one coming to this side and the orange one here. So usually it is never that simple, right? So using the kind of the one odd color out, which is the black here, the closest number to that would be the number 2. So let's see our resistance reading on that one. So we have 2.2 ohms from black to red. So let's go from black to orange, because that's the next color up. 2.3 ohms. So you can pretty much say that this is going to be 2.4 ohms when we touch that, right? 2.4 ohms. So we can already see that this is the closest to this one here. The resistance is the closest to the black. So if we go on here and draw 2 taps, so there's a tap here and a tap here. So this one here would be black. The closest to that one is red. The next one up is orange and yellow. And those would be the taps on this. Now, how do I know that these ones are so close together? Well, if we look at this, we can see that red is the furthest away from black, right? From this point here, at this point of the winding. If we had the winding this big, this is the actual furthest winding away, like right from black would be the yellow. But we can see as a start, this was the furthest away at that point. So we can see that that's the furthest right there, right? You can see it's going to be about 2.2 ohms. So there's quite a gap between black and red is what I'm saying. If we test the continuity between these leads here, it's going to be really low. So let's just, for fun of it, test from red to yellow. So let's go from red to yellow. You can see that it almost looks like a dead short. Or if we test from red to orange, of course, it's going to look like a a really low resistance there, right? But if we go back from orange to black, you can see that it's further away, so we're going to have some resistance there. You see that? We have 2.3 ohms, right? So what that's telling us already is these taps here, they're close together, right? Because we had, 2.2, 2.3, and 2.4, right? Or around that. We know that these taps here are going to be close. So this is most likely going to be, say, 110, 115, and 120. Or say 115, 120, 125, something like that. That's most likely going to be what this is right here. And the way to really determine that is to load the secondary side with an appropriate load, and then we can adjust these taps here until we can get the voltage correct on this side for the filaments. You see, whenever you're dealing with an RF power tube or some really large audio amplifier tubes, some big audio power tubes, having the filament voltage on those tubes is really, really crucial, having them correct. So say it's a 10 volt filament, you want it at 10 volts for the maximum amount of life out of that tube. And a lot of the times these transformers here, they'll give you multiple taps just to move around to get that right. So even say the line voltage was at 115, all right? So you had 115, and say it was just a little high on this side for some reason. Say one of those power tubes that you're using didn't draw as much current as it really needed to. So what you could do is you could run that at the 120 tap to drop it down on this side. Now, moving the taps around on this side, since they're so close together, really isn't going to cause much heating in the transformer. Say you were to run from black to red or from black to yellow, the difference in the heating of this core is going to be really quite minor because it's such a large transformer and the taps are so close together. They're really, really close together. So some more hints and tricks. I'll show you more about this down the road and how you get to understand this a little bit better. So since we know this side now, we need to figure out this side. So that's going to be really easy. So we know that we have... Let's get these out of the way so it doesn't get too confusing. Move those out of the way. So we know that we have brown. We know that we have a red, an orange, and a yellow here. So we know that the brown is the odd color out. So if we go to red, we're going to see a large amount of resistance. Now keep in mind that the resistance readings of both of these windings may differ a bit. That's just the way it is in transformers. All right, so this one is going to start at, say, 2.5. So that's the red lead. So orange is the next one, so this is going to probably be 2.6. There it is. And then the next one's probably going to be 2.7. And as you can see, it's 2.7. So we know that already. So this is following the exact same order here. So what we would do is we would write brown here, or like this, and then we would have our two taps here. Again, we have yellow, orange, and red, but the difference is that this is going to be black, yellow, orange, and red. So we know that that's how this is going to work. Now, if we want to connect this to, say, a 120 volt supply, what we would do is we would connect these two leads together. And to start off, I would start at the center tap. So we'll start with, say, the orange. And what we would do is we would connect the orange lead, this one here, over this here to the orange lead, and we would have our other lead out like this, and then we could measure the voltage here. The voltage with no load is going to measure high on this side. It's not, just say this was a 5 volt tube or something like that. Say this winding is rated at 5 volts. We don't know what the secondary is on this is yet. So say this was at 5 volts, kind of common for some of the larger tubes. With no load on this side, it's going to be close to 6 because there is no regulation here, right? The only thing that's happening is you put load on this side and it drags the transformer down. So that's the way it is. Whenever you're designing a transformer, you always have to design them high, because if you this say put out exactly 5 volts with 120 here, if you put 5 volts at, say, 10 amps on here, this is going to drop down to probably 4.7, 4.6. It's going to be way off. So you always have to design this a little bit higher. And that's the art in winding transformers. Down the road, we're going to wind some transformers together. We're going to definitely do that. I'll show you how to wind your own filament transformers or power transformers for, say, a linear power supply. So you wanted to make a really big 13.8 volt power supply and have lots and lots of pass transistors. You can wind a transformer for that as well. It's really quite simple. So at any rate, we'll get into that down the road. So what I'm going to do now is I'm going to test this and let's verify. Let's see how many volts is on this side right here. So that's what I'll do. So basically what I'm going to do, since this is the odd color route, we know that these are going to be connected for parallel connection. So what we would do is we would take the brown and the black and say twist these together like so. And we have the orange and the orange stripe, which we would twist together like so, and that would hook both of our windings in parallel. And what we can do now is measure this. So we would start doing that with a dim bulb tester, getting these other ones out of the way. So I'll get that all set up and I'll be right back. I have the transformer attached to my isolation transformer, Variac, and current limited supply with some dim bulbs in line right now as well. So if you're following along in this procedure, you're doing so at your own risk. If you're unsure of what you're doing, definitely do not do this procedure. So I have the orange and black stripe lead twisted together just like on the schematic here, and I have the brown and the black lead twisted together so the two windings are in parallel. And I've also got some dim bulbs in line right now so I can monitor the current just in case something is wrong. So what I'm going to do now is turn on that supply. So there's AC on that winding right now, and the Variac is turned down really low, and I don't even have a glow on the bulbs yet. So I'll turn this up, and they're just ever so slightly glowing, and that's at max right there. So if I click the dim bulbs out of line, there it is, 5.8 volts. So you can comfortably say that that is a 5 volt winding. And then of course when you load this side here again, it would draw that down. So definitely those taps are to be able to adjust this side here. Now there's a lot of current available right now. It's only 5 volts, but there's a lot of current available right here. If I was to touch these two leads together, I would have an incredible spark on this side right here. So some pretty high current available at this point to light up some pretty large RF power tubes, I'm pretty sure at this point. So the transformer is working, and now that I've got this all written down on this piece of paper just below, I'll save that and catalog that with that transformer so next time I don't have to do this again. Let's determine the impedance of this audio transformer right here. So we can clearly see it says 0 and 8, so this is designed for an 8 ohm speaker. So if I measure these two leads here, what should my DMM say? So let's take a measurement and see. It says 0.6 of an ohm, so that's under 1 ohm. Well, why does this say 0 and 8 ohms, and this is measuring under 1 ohm? The reason being is we're using a meter that measures only DC resistance. This is an AC resistance measurement or impedance measurement. They're two very, very different readings. This is where a lot of people get this confused in the audio world. So, for example, one of the things that really doesn't help a whole lot is if you have an 8 ohm speaker and you measure it with your DMM, a lot of the times it will measure around 6 ohms. So people just think, oh, there's a discrepancy between my meter and the speaker, or the speaker's wound a little different or something like that. Well, no, it's not. The speaker is actually 8 ohms. It's just that you're measuring it with a DC meter, so it's showing 6 ohms. That's the difference. So that really doesn't help. And I find this confusion a lot in the audio world. Now you can see 0 and 8 ohms on this side here, but that's not fixed. You can put a 4 ohm speaker here. The differences will be reflected on this side, the vacuum tube side. And this is the golden nugget today. You're going to see in RF systems why changing the load will affect the RF power amplifier or will affect the other side. I'll get more into that when we do the calculations here. So these are still useful measurements. If you know the measurements, say, on the plate side here, so we measure this right now, we'll get a DC resistance of about, say, 212 ohms. So if you know that, that's helpful. If, say, you're verifying a bunch of these things in an audio amplifier, you know that's supposed to be, say, 212, something like that. You can go and test the next one. If it's 211, 210, something like that, you know that chances are it's okay. If it was 50 ohms, 45 ohms, something like that, you would know that there's a definite problem inside the transformer. So DC resistance readings are useful, but they are not all that useful if you're a tube amplifier designer and you need to design something around a chunk of iron that you already have. So we want to determine what this chunk of iron actually is, what its impedance is, and that's what we're going to do here in just a moment. In order to determine the impedance of this transformer, the very first thing that we want to do is figure out the turns ratio inside this transformer. And that's pretty much all we need to work out our impedance, and that is quite a simple thing to do. Now, figuring out the turns ratio involves the use of voltage on this side, so if you're following along, you're doing so at your own risk. I'm using my isolation transformer variac and dim bulb supply to feed this side so that we can make that measurement, and I'll show you exactly how I'm going to do this. So what I'll do is I'll attach this to my supply, which is off right now, and what I'm going to do is grab the leads to my meter, and I'm going to put them at the speaker terminal side here, just like so. What I want to do now is turn up my variac supply until I get 1 volt right here at the speaker outputs. So I'll turn this on right now, and I'll start adjusting that up. Until I can get as close to 1 volt as possible. So I'll turn this up. Gets kind of touchy right around 1 volt. Because I want that right at 1, or close to. That's close enough. So now that I know I have 1 volt at this side, I want to measure the voltage on this side. So I'll remove this and carefully attach this to this side here and this side right here. I don't think that's attached. Hold that right there. Well, that's a nice turns ratio. That's pretty accurate. So we'll say 25 volts. So 25 volts for 1 volt. So we'll just shut the supply off. So what does that tell us right now? Our turns ratio is 25 to 1. That simple. 25 volts on this side gives us 1 volt on this side. Now you take 25 and square that. So if we go on here, we go 25 squared equals 625. So we have 625. Now this is the number that you could actually write on the audio transformer, because once you know this, you're pretty much good to go. Now that we know 625 here, we can see 0 and 8 ohms right here, right? So all we do is we go times 8 ohms. That's it. 625 times 8 ohms equals 5K. So we know that the impedance of this side of the transformer is 5K. That easy. So if we draw the transformer here, real messy like, this is the speaker side. So we know that 8 ohms here gives us 5K ohms on that side. It's just that simple. So all you need to do is figure out the turns ratio. So now, here's that little golden nugget I'm telling you about, and this will help you understand how things change. So even though this is 0 in 8, that's not fixed. I can put a 4 ohm speaker on this side. What's going to happen? It's going to reflect to the impedance on this side. So let's take this number and go times 4 ohms. So if I go clear, so we go 625 times 4 ohms equals 2.5K. So now the impedance on this side has changed to 2.5K. So for a 4 ohm system, we get 2.5 on that side. So just say you had a vacuum tube or vacuum tube system that would be comfortable operating at this. Just run a 4 ohm speaker and you have the transformer for it. So you can see how changing the load impedance will affect to the actual driving side. It's the same thing in RF systems. In a 50 ohm system, if you have the impedance on the output side, it's way off. That reflects back to the driving side, and that causes problems with the finals. And this is the thing with transformers. So there you go. It's just that easy. Same thing with any other transformer. If you wanted to work out the plate-to-plate load of a push-pull transformer, you would just go end to end. That's the plate-to-plate load. So you would take your supply and put the supply on this side. A lot of people like to take the supply and put it on this side, and it'll step the voltage up, and they read the stepped up voltage. Either or, you can go either way. It's just that, you would feed this with 1 volt worth of signal to read this one side. It's just whatever you're happy with. I find that when I do it this way, it's an easier process, and you get really accurate on the 1 volt side by doing that, by moving the variac around. Now keep in mind, again, if you do this, you're doing so at your own risk, because there is exposed voltages on this side here, and depending on the transformer, it can get pretty high on this one side. So that's how you determine an audio output transformer's impedance. Boy, that's sure a lot different than 212 ohms, right? What was this, 0.6? So that's the DC resistance, right? 0.6 of an ohm and 212 on this side. Look at the difference between the impedance measurements and the DC resistance measurements. So there you go. I hope you found this useful. If you did and you enjoy these videos and you'd like me to go further into this, further into testing audio and power transformers, let me know below in the comments. And again, if you enjoyed the video, you can let me know by tapping the heart symbol below. So until next time, take care. See you soon.